All right, so we have been working in hyperbolic geometry, and we left off last time with kind of an odd thing to write down, at least in terms of Euclidean geometry. It felt like a very odd statement to write down. So let me get to our screen where we were. It was proposition 6.2, and we said something like this. When we're working in hyperbolic geometry, similar triangles must be congruent, right? And of course, that's not true in Euclidean geometry. And we are going to start with a proof for that fact today. So let's take a look at why this must be true. We're going to do this by assuming the contrary. Okay, so I kind of like those kind of proofs. I find them to be a little bit more easy because you're looking for some kind of a contradiction in them, and it works very nicely for this one. So we're going to assume the contrary. That is, there exist triangle ABC and triangle A prime, B prime, C prime that are similar and not congruent. Okay, so tell me what it means to be similar. We haven't really talked that much about similarity in this class. So what does it mean for two triangles to be similar? Fabulous, and that's actually the fact that I'm going to write down next. Yeah, so they have the same shape, right? So in general, it would mean they wouldn't have to have the same size overall, but they have the same shape, and in terms of triangles, that means all the angle measures are the same. I don't want to say it that way. Let me say all pairs of angles are congruent, because we're not talking about equilateral or English angles, right? Not necessarily. Okay, well, it has to be true that none of the sides are actually congruent, because if we had a pair of sides that were also congruent, then we'd have angle side angle, which is a congruence criterion, and then triangles would be congruent, right? So there must be no pairs of sides that are actually congruent to one another. Okay, so we've got unequal side lengths. So we have either that the side lengths of one are larger or smaller than the other one. And so we're just going to make an assumption that it's larger. If it were smaller, we would just switch the order of the triangles. Does that make sense? One of the triangles is going to have a larger side than the other one, and in fact, it's going to have two sides that are larger. Okay, without loss of generality, we can do that. So at least two sides of one triangle are larger than the two corresponding sides of the other. All right, so I'm going to give you an acronym. Maybe you've seen it before. It's WLOG. And I'm going to write it out for you. This is without loss of generality. We're going to make an assumption about which one's bigger. If it were the other way around, we'd just switch it. So we're going to assume that side AB is bigger than side A prime B prime. And side AC is bigger than side A prime C prime. And let's draw a picture so that we have a way to reference these visually as well. I'm about to switch slides anyway, so let me go ahead and draw my picture over here. Okay, so here's our two triangles. I shouldn't have done it that way. They said one of them was actually bigger, so let's go with this one. All right, so here's A prime. Let me draw my picture the same way it's in my notes. A prime, B prime, C prime, and then here's A, B, C. So AC clearly bigger than A prime, C prime, and so forth, right? So there's facts are there. All right, so there exists a point we'll use a little bit of symbols in here. There exists a point B double prime on AB and C double prime on AC such that A B double prime, not a space, is equal to A prime B prime, and A C double prime is equal to A prime C prime. So over here, all we're saying is that there is in fact a point. Here's A, B is what I meant, sorry, B double prime, and here's C double prime. And it is in fact true that A prime B prime and A B double prime, and then these two have these congruences. Make sense so far? Okay. Now, I could actually then create a triangle here. So notice if I connect the B prime, B double prime, and C double prime, I create a triangle. And that little triangle that I just created is actually congruent to the other triangle. How come? Close. Side angle side. Okay, so I've actually got a congruent triangle set now. Okay, so that's what we're going to write down next. So then A prime, B prime, C prime, and I meant to put triangle in front of that. Let me move that. So triangle is actually going to be congruent to triangle A, and then it's B double prime, C double prime. And like you guys said, it's by side angle side. Okie dokie. So are you ready for a contradiction? Because it's really fast coming now. Hence, therefore, thus, whatever word you like. Hence, corresponding angles are congruent. So if I want to mark a few of those, we had this angle right here, congruent to this angle, and now it's congruent to this angle, right? All of those are congruent to one another. A at the top is congruent to itself. I'm not even going to mark it because it's really, at least at the moment, not all that useful. And this piece right here, C and C double prime and C prime are all congruent. So we've got these pairs of congruent angles here. By the alternate interior angle theorem, we called it AIA before, and if you want to reference it, it's on page 162. That actually means we've got some parallel lines. So BC is parallel to B double prime, excuse me, C double prime. And that makes this quadrilateral B double prime, C convex. But this quadrilateral, oops, B double prime, C double prime, C, trying to get those in order, has an angle sum of what? Can you guess? 360. Let me speak to that just a moment, but if that happens, we've got a contradiction, okay? So as you're taking a look at your diagram above, you have these supplementary angles, right? So this angle right here, the blue one that I just marked, and the other one are 180 added together, correct? We've got the same thing going on over here, which is where the 360 is coming from, is because of those supplementary angles and those parallel lines. So we've got a contradiction, and what this means then is in hyperbolic geometry, angle, 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 which is what you told me what it means for triangles to be similar, right? Angle, angle, angle is a valid criterion for congruence. Of triangles. That leads us pretty nicely into talking about parallel lines, because we actually used those inside of that proof. And so we're going to shift to talking about parallel lines within hyperbolic geometry. When kids first learn about parallel lines, one of the ways they will often describe parallel lines is them being equidistant from one another, right? And then once you get into a more formal geometry class, maybe it wasn't even in high school, maybe it wasn't until you got to this class, or thinking about it in a trigonometry class or something, somebody talked about the fact that that's really not what we mean by parallel. Really, equidistance not a very good description. We talk about it as being lines that never intersect. So we're going to move into that sort of perspective of equidistant business with parallel lines inside of hyperbolic geometry next. So our sort of title for what we're talking about is these are parallels which admit a common perpendicular. Okay, it's a little small. I'll try to write a little bit bigger. We're going to start with the definition. Given lines L and L prime, and points A and B on L, drop perpendiculars A prime, and B prime to L prime. We say A and B are equidistant from L if A prime is equal to B prime. And remember that notation without any symbols on top means length or distance. So picture-wise, if we have, well, we'll try with that one, these two lines, L and L prime, with points A and B on L. If we drop a perpendicular down to L prime, so that these are perpendicular here, that's what it means. We've got our A prime here and our B prime here. If these lengths are the same, then we would say they're equidistant from A prime, B prime. It's important where I put the perpendicular notations, because it's actually not true that this is our picture, correct? Why not? Because we're in hyperbolic geometry. Exactly. There's no rectangles, right? No rectangles. So we don't have those two perpendiculars at the top. Okay, good. I'll do it on a different screen so that I can do my proof and my theorem on the same one. Theorem 6.3. Using this definition, if in hyperbolic geometry, if L is parallel to L prime, then any set of points on L equidistant from L prime has at most 2 points in it. So my picture that I drew before, where I had A and A prime and B prime, basically what we're saying is that I couldn't have a C and a C prime with that property that all three of those would work and be equidistant from line L prime. So we're going to prove this by showing that if I did have 3 points, it would create a contradiction. That's how we're going to prove this, okay? All right, so another acronym for you, BWOC. Why do you think it stands for? By way of contradiction. Very good. So I'll let you jot that down. By way of contradiction. We're going to assume 3 points A, B, C on L are equidistant from L prime. We may assume that B is between A and C. There's some kind of an ordering, so we're just going to go with alphabetical. And we're going to let A prime, B prime, C prime be on L prime as the feet of the perpendiculars from A, B, C, respectively, to L prime. Begging for a picture, I know I am, so we're going to draw it. So here's L and L prime, A, B, C, and I have these three perpendiculars to the points A prime, B prime, C prime. So far, so good? Okay, good. All right, this gives us three Sakari quadrilaterals. We have quadrilateral A prime, B prime, B. So this is the rectangle that's on the left. Over, oh, I can't make it sideways. Okay, over here, there's that quadrilateral. We have the quadrilateral on the right, which would be quadrilateral B, B prime, C, B, B prime, C prime, C. And we have the one that would be sort of on the outside of all of it, right? So quadrilateral A prime, C prime, C. By proposition 412, that's from page 177, the summit angles. What can you tell me about those? Do you remember? Summit angles of a Sakari quadrilateral. Yes, they are congruent. So they are congruent to each other. So at the top of my diagram here, I've got lots of little congruent angles, right? I've got this one. That's not what I meant to, how I meant to draw it. Let me try drawing it a little bit more curved. So this one, and this one, and this one, and this one. There's four of them, and they're all congruent to one another. So this would be angle A prime, A, B is congruent to angle B prime, B, A, congruent to C prime, C, B, and B prime, B, C. Hopefully I got all those written right. If not, you've got your picture that shows them, right? The 4 yellow ones or orange ones at the top are all congruent. We talked about creating problems, if you will, with supplementary angles on our last proof, and the problem is going to come from the same place here. Since angles B prime, B, A, and B prime, B, C are supplementary, what's going to happen? This sum equals 180. What will they individually? Yeah, they're right angles. These are 90-degree angles, or they're right angles, or whatever kind of phrasing of that you want. Why is that a problem? Say that. Yeah, Kelsey's right. Now I've got rectangles, don't I? Yeah, all of those orange markings that I have at the top, we've now said are actually 90 degrees. Just because that one right here, I didn't mark it, but I can, this spot right here created supplementary angles that are congruent. Supplementary congruent angles must be 90, so they're all 90 at the top, which means I've got rectangles. That's a problem. So thus these quadrilaterals are rectangles. And I don't have space to do it, but I'll try it anyway. Make it just a little smaller. That's a contradiction. No rectangles. No rectangles. So what does that mean I have then? I mean, what we've said now basically is that if I have 2 points, they can be equidistant if they're on a parallel line, but not if I have more than 2. So what are my sort of possible scenarios visually? How can I think about this to make it make sense? Because if I draw the parallel lines the way I'm used to drawing them, it becomes very difficult for my mind to sort of agree with the fact of what I just wrote down mathematically. Does that make sense? I mean, it looks like they're equidistant, so what's the problem? How do I draw this instead to make my mind believe what my math just said? So this allows for 2 possible scenarios. Okay, so one possibility is that I do in fact have 2 points equidistant, because remember the theorem said at most 2. So if I want to draw that picture and what that would look like, here's my line, L prime. And you're not going to probably like this very much, but here's my line L. And all of a sudden now we're like, yeah, lines don't have to be straight. That's our impression of them, right? I mean, when we're talking Euclidean geometry, I get frustrated sometimes with students who keep saying straight lines, straight lines, straight lines, because lines are straight. That's by definition what we mean. But that's not by definition what we mean in hyperbolic geometry. So now we've got what looks like a curved line, right, Seth? Indeed. So let's actually take a look at what happens here and why at least it will help us with this equidistant sort of issue that we've got. Here's point A. Here's my point at the bottom, A prime. And if I sort of measure these off right here, we could take this point over here. Looks like it's about right there. And that would be B. And at the bottom, B prime. And visually speaking, there's not another equidistant point from line L prime. I mean, I don't see one. Now if I draw it like this, right? If I can get beyond the fact that lines are not straight, this picture at least fits with that theorem now. And so if I measure this, here's my distances. And if I had any other particular point, so let's say we had C here, and I measure down from C to C prime, it's not going to be the same length. Now there will be another one, right? That's the same length as CC prime. Yeah, there's another one on here. Let me see if I can kind of picture where it would be about right there, I'd say. And so I can draw another one in that's going to be, and we'll just call it DD prime, that's going to have the same length as CC prime, but they're not going to be the same length as A prime or BB prime. Because this is one possible scenario. This is the scenario where pairs of points on L equidistant from L prime exist. Now, over here, this theorem doesn't say that there have to be 2 points. It says there's at most 2. So what does at most 2 mean? It means it could be 2 or what? Or 1. Now, if I say 1, it doesn't sort of make sense, the structure of the English, right? There's 1 point equidistant. So what would that really mean if there's not 2? There's none. I mean, that's what it would really mean. So that's my second scenario. So my second scenario, visually speaking, would look like, here's my L again, and L prime now looks like this. You could almost imagine there's somehow like an asymptote kind of thing going on there, right, as it goes closer. But we have these pair of lines now. We have point A, and we have A prime down below. And then any other point that I pick, we'll call it B again, down to B prime, and of course these are creating right angles by definition. They're not equidistant. So in this scenario, like you guys came up with, there are no pairs of equidistant points, or we can say no pairs of points are equidistant from L prime. And interestingly enough, each case is possible in hyperbolic geometry. So that's fun. That's a fun fact. All right, let's take a look at Theorem 6.4. Continuing this idea of being equidistant. In hyperbolic geometry, if L and L prime are parallel lines, for which there exists a pair A, B on L equidistant from L prime, then L and L prime have a unique common perpendicular segment between L and L prime. Okay, I don't have a picture drawn on my notes, but we got to draw a picture, right? Absolutely. All right, so here's L prime. Our picture will look like the first one that I drew on the previous slide, like this. And we have A, B, and here's A prime and B prime. And we're going to start with the proof. This is our setup right now. This is what it's so far has described. Suppose A and B are on L equidistant from L prime with feet A prime and B prime respectively. Then, quadrilateral, A prime, B prime, B is what type of quadrilateral? Yes, Sakari. Is a Sakari. Quadrilateral. And we're going to let M be the midpoint of AB. And M prime, be the midpoint of A prime, B prime. So I've got I don't attach them yet, but here's M and here's M prime. By proposition 412b, M prime is perpendicular to both L and L prime. So when I draw this in, I actually have a perpendicular, here and here. What kinds of quadrilaterals did I just create? Do you know? We've had only two types, Sakari and the L one, yeah? Lambert, you know, like the Throat Rolls place, Lambert's. You guys never been to Branson, huh? I would suggest you go. It's good. It's in Springfield, actually, I think. It's not actually in Branson, but it's good. All right, so moreover, quadrilateral M prime, B prime B is a Lambert quadrilateral. Trying to figure out how I want to write this because I don't like the way it's written in my notes. And angle B is acute. We know it's not right, because we would have a rectangle, so, and we know it can't be more than 360, so it must be acute. So angle B is acute, implying, that was too many, implying, there we go, implying M prime is less than B prime. Right? The length of the segment that's in the middle is the shorter of the two. And that's actually by proposition 413. And this is true for any point on L. We didn't create it in a special way, okay? So M prime is the shortest segment between L and L prime. One more fact has to do with the fact that it said it's a unique common perpendicular. So since rectangles don't exist, D and E do not exist, like back from algebra, right? Or calculus or something. Rectangles do not exist. M prime is unique. Can't have two of them or we'd have a rectangle. So we do have shortest distances between parallel lines. We can possibly have, and that only happens if we've got pairs of equidistant points, right? We can have pairs of equidistant points, and if we do, we will have a shortest distance. Theorem 6.5 is kind of going to close our discussion about the parallel lines and the equidistant issues, all right? Theorem 6.5. In hyperbolic geometry, if L and L prime have a common perpendicular, and we're going to give that segment name M prime, just like we did before, then L and L prime are parallel, and M prime is unique. Moreover, if A and B are on L with M the midpoint of AB, segment AB, then A and B are equidistant from L prime. Does it feel a little bit like the converse of the last thing we did? You're starting with the conclusion and you're going back to proving the hypothesis from the earlier argument. Yeah, it is. So let's take a look at proving this one. Let me draw the picture first, I suppose. That's what I've been doing. Okay, so let's draw our picture, just like we have been drawing it, with our curved line. We have A, and we have B, and we've been told that M is their midpoint, so this is the picture that we have right here. And we know that we have these perpendiculars dropped. What we're trying to prove is that those distances are equal. Do we have an MM prime? We do. So we've got one more perpendicular dropped. Okay. Now let's write down that setup. So let's see, by angle, the alternate interior angle theorem, AIA, L is parallel to L prime. So we get that almost for free. We've got the congruent alternate interior angles. We don't have to work for that one. If L and L prime had a second common perpendicular, there would be a rectangle. Okay, so it's unique. So we've got a unique segment. That's not a problem. Now suppose M is the midpoint of AB. On L and drop perpendiculars A prime, and B prime to L prime. All right. And I'm actually going to draw in something that we haven't worked with today, which is a triangle. So I'm going to draw this dotted line in here and in here. then triangle AMM prime is actually congruent to triangle BMM prime. Why? Yeah, side angle side. Does everybody see that? The side angle side that it's referencing? Okay, good. Hence, AM prime is congruent to BM prime. So that's the dotted lines I drew in. We've got those congruent. And angle A prime M prime A is congruent to angle B prime M prime B. I wrote this wrong. I was on the wrong line. I'm so sorry. Let me fix it. It's like, that's not right. You don't have to erase everything. You're almost good. A M prime M and B M prime M. Okay, so it should be these angles that I was referencing. Okay, those are also congruent. And of course, both of those statements are because corresponding parts of congruent triangles are congruent. Therefore, we actually do have the angle I was trying to write before, angle A prime M prime A is congruent to angle B prime M prime B. I'm out of space here, but I'll flip to my next screen to finish the Y on that. The reason is because they're complementary to congruent angles. Right, because we have 90-degree angles actually happening down there at M prime. The two that I marked, I know they're congruent, so the other two that are making up that other pair are also going to be congruent here and here. So now what do you think we can say? We eventually do, but we're going to do it with triangles before we get there. Do you see the bottom triangles now? They're going to be congruent. Why? Okay, so let's figure out what we have. I've marked my orange angles, correct? And we know that the dotted sides are the same, right? And we've actually got another angle marked, the right angles in the bottom. So what do we actually have here? We don't have the three sides because I don't have the sides on the perpendicular, like vertical sides marked. They're not marked. And neither are the sides on the bottom. They're not marked either, right? We don't have all three angles. Angle, angle, side. And I think you said side angle, angle, which is the same thing. We usually list the angles first for some reason. I'm not sure. But what we've got here is we've got this angle, and then this angle, and then this side. So you usually see it written as angle, angle, side. Yeah. So our triangle's at the bottom. So triangle AM prime A prime is congruent to triangle BM prime B prime, and that is by angle, angle, side. Thus, like Shayna said, we've actually got these rectangles now with all these pieces congruent, which is what we were kind of intending, but only for the purpose really of saying that those perpendicular pieces on the sides are equidistant, right? So thus A prime equals B prime. I.e., what that means then is that A and B are equidistant from L prime. Okay, so this is the last little piece in this section, and there is one homework problem for you. I also sent an email out last week as a reminder about there's a GeoGebra assignment. When's that due? Tuesday. So Seth's like, wait a minute, what email? Yeah, there's a GeoGebra assignment due on Tuesday, GeoGebra assignment number 3. So we're not having class on Thursday, so maybe that's a good opportunity for you to get some of it done if that's what you need to use it for. So you have GeoGebra due, and you're going to have one homework problem from this section as well. So this will be due on Tuesday too. So this is page 271. It's problem number 4. And that will be due Tuesday, which is April 17th. I feel like my 1 and my L are running into each other. I'm happier with that. Okay, we're not done for today. We've still got 10 minutes, so I'm going to start the next little bit. All right, so hold tight. We won't get very far into it, but we can get started, so we will. All right, what we're going to take a look at next, still in hyperbolic geometry, we're not leaving here for a little while, is limiting parallel rays. This is Theorem 6.6, so we're adjusting direction a little bit, but continuing on in the same chapter. And it says the following: for every line L and every point P not on L, let Q be on L such that segment PQ is perpendicular to L. Then there exists two unique non-opposite rays, PX, PX prime, on opposite sides of PQ, that do not meet L. So no intersecting. And for which any ray PT will meet, or you could say meets. So we'll meet L if and only if PT, the ray, is between PX and PX prime. Moreover, these limiting rays are symmetric. About PQ i.e. angle XPQ is congruent to angle X prime PQ. Let me draw a picture of what we have going on. I'll write one note and then we'll pause for today. So here's line L. Here's point P, not on L. I can drop a perpendicular just like before because it's not on L. There is this perpendicular to here and it's meeting at Q. What this is saying is that there is a ray over here somewhere and a ray over here somewhere, and they are non-opposite, so they don't form a line. Okay, that's what it means. If they were opposite rays, they would form a line. Okay, these are non-opposite rays. One of them, I'll put it on the left, is PX. The other one is PX prime. And we're saying that if these are, in fact, the limiting rays, any ray that occurs in between them, sort of under them in my picture, would at some point meet L. So if you want to draw those two rays that I drew sort of like they're curving, that might help you to sort of believe your picture a little bit more, right? But the image you would have here then would be that if I had another ray in between, like this one, they would eventually cross. And so there's ray PT in between, and it's actually crossing. Okay, one more piece that it actually mentioned in here is that this angle and this angle are congruent. Okay, that's the symmetric about the line or the segment PQ. So one note before we quit for today. Note, PX, ray PX, and ray PX prime are called limiting parallel rays. All right, we will pick back up where we're leaving off right now. There's just a couple more pieces in here, and then we'll be moving on to some classifications when we meet when? Tuesday, that's right.